Welcome back. In this video, I'm going to quickly talk through the 2024 VCAA Specialist Math Exam 1. And as you know, this paper is a tech-free paper, which is 40 marks long, and the student will have 15 minutes reading time and an hour writing time. And the VCAA will supply an official VCAA formula sheet. So this slide with my suggested solution is prepared independent of VCAA. And a VCAA reserves all rights to the exam materials. And if you want to, let's say, find out any further information, please refer to the assessment report to this paper. By the way, VCAA has uploaded the marking guide to assess this paper as well. So you can access the published marking guide on the VCAA website. So here is the front page. The first question considered the function with the rule fz equals to 3z to the power 3 plus 2iz squared plus 3z plus 2i. And this z is a complex variable. First part of the question wants to verify that 3z plus 2i is a factor of f of z. So basically, if you observe the structure, you can easily see for the first two terms, there is a z squared as a common factor. And then for this guy here, 3z plus 2i, it's just itself. But more than likely, we wouldn't get some student to write down, let's say, what's the z value if you equate that to 0? That is z equals to minus 2i over 3. So if you substitute minus 2i over 3 into the function, you'll be able to get eventually like a 8 over 9i minus 8 over 9i minus 2i plus 2i equals to 0. Of course, this is a 1-mark question. And we know by factor root theorem, the remainder should be 0. Therefore, it is important for the student, in my opinion, to actually calculate, substitute and calculate. And it clearly shows this chunk of calculation leads to 0. Of course, if you directly factorize the polynomial by grouping, yes, you can see z squared out, 1 out, and 3z plus 2i is a common factor. So apparently 3z plus 2i is a factor. And part B, hence or otherwise, we want to solve the equation fz equals to 0 and give your answers in Cartesian form. There are so many possible approaches, I must admit, but having said that, the complex conjugate root theorem does not apply here, or at least we should not apply conjugate root theorem to the minus 2i over 3. Because you can see the equation does not purely have real coefficient. This is a 2i component, even though we can get, let's say, z squared plus 1 equal to 0. And yes, this is a conjugate pair. If you derive another solution, z equals to 2i over 3, nah, that's not the case, because we don't have another conjugate linear factor after 3z plus 2i. Therefore, z equals to minus 2i over 3 stands alone. Alternatively, you may want to use, let's say, some sort of long division. And just notice if you are going to put minus 2i over 3 here, what you factorize out is z plus 2i over 3 rather than 3z plus 2i. And the other quadratic polynomial will be 3z squared plus 3. Yes, you could push the 3 to the other linear factor, but eventually you just get a plus or minus I from the second quadratic factor. I would like to mention a special technique because this special technique is not widely known. It's called Vieta's theorem, or we could say this is the relation between the coefficients and the roots of certain polynomial. Vieta's theorem states that if you have a polynomial in the general form, and all the terms are listed in descending order in terms of the power, then you can identify, for example, A is 3, B is 2i, C is 3, and D equals to 2i. For the 4 terms, their coefficients. And Z3 equals to minus 2 over 3i is something we obtained in part A. And then the sum of the solutions will be negative B divided by A. So Z1 plus Z2 plus 3 equals to minus 2i over 3. And one of them must be minus 2 over 3i. Therefore, you can sub that in and get the relation between Z1 and Z2. If they add up, it's equal to 0. Also, the product of the three roots available will be minus d divided by a, which is minus 2i over 3 as well. So if you sub in minus 2 over 3i as z3, you will be able to get z1 times z2 equals to 1. So this is the second equation you can use to derive, okay, the z1 and z2. Basically, z1 and z2 must be conjugated of each other because if you think about 1 times 1, yes, that's 1, but 1 plus 1 is not 0. Therefore, the only possibility is I and minus I. So minus I squared equals to 1. So these two will satisfy the two simultaneous equations we derived. But this is a very extreme method. I'm not recommending using this method because if it's a more complicated equation, it may involve more complexities and you may make mistakes. Part C. We would like to plot the solutions of fz equals to 0 on the Argand diagram below. So you will need to mark the 3 points accurately. So make sure they're really hitting the intersection between the circle and the axis. For example, it will be 0, 1, 0 minus 1, and a 0 minus 2 over 3i. And it is also common for the examiners to see students labeled some solutions along the real axis, which is problematic because the 3 solutions are all purely imaginary. Okay, question 2 was a very nice and simple direct proof question. The reason why I stressed this phrase, a direct proof, is because a direct proof should not include induction, contradiction, nor should it include contrapositive. So induction, contradiction, and contrapositive, the 3 proof techniques here are indirect proof. So what does it mean by direct proof? Well, you just get straight from the condition x is an odd integer, and then do some algebraic manipulations on this quadratic expression and show it is in the form, let's say, 2p plus 1 whatsoever. Here is one possible method. You could argue x equals to 2m plus 1 or 2k plus 1. But remember, when you are talking about integers, you must specify your parameter like m belongs to z. Sometimes if you write m belongs to r, then the condition must be real number rather than integer. So you have to identify the correct domain restriction, not all real numbers here. Then you make a substitution into the 3 terms. Make sure you use brackets to avoid any algebraic errors. And you expand the first line to get 8n squared plus 8n plus 2. So make sure you use your perfect square correctly. And then expand the negative sign into the 2 terms and then collect minus 7 to the n. Finally, you'll be able to get 8n squared plus 2n minus 8. So to make your proof clear, you need to take out a common factor 2 because your target is to show this is an even number, a multiple of 2. And if you want to introduce a new variable or new parameter, make sure you claim it clearly. Let's say let p equals to 4n squared plus n minus 4. By the way, this should be a 4 here. I'll fix that later. Belongs to z. And therefore, it's 2 times some whole number. Therefore, the whole expression is an even number, okay? Alternatively, if you use 2n minus 1, this does the same work except for a small variation in the final expression you are going to write down, okay? And yes, you are required to take out the 2 as a clear common factor to confirm the desired conclusion. Alternatively, if you look at the assessment report, here is a very rare approach by some students. They could argue that, okay, 2x squared minus 3x minus 7 is like x times 2x minus 3 minus 7. But then they have to argue very carefully because x is an odd integer and 2x is an even number. When an even number take away 3, it's an odd number. And also the minus 7 to the n is an odd number. So eventually you get a product of two odd numbers, subtracting an odd number. And the product of two odd numbers will be an odd number as well. So the difference between two odd numbers must be an even number. Therefore, 2x squared minus 3x minus 7 must be an even number. So I would say I prefer the safer approach is here, okay? Question 3. Question 3 has 3 parts. Starting from a function in perfect square form, a ratio, a rational function, x minus 1 squared divided by x plus 1 squared. And the question nicely gives us a hint in a fully decomposed partial fraction form. F of x is a plus b over x plus 1 plus c over x plus 1 squared. And a, b, c are integers. So we want to show that a equals to 1, b equals to minus 4, and c equals to 4. 1 mark. So you have to show a set of convincing working, whether it be separating algebraic manipulations or combining the 3 terms using the given 3 numbers, or let's say using partial fractions or matching coefficients. Let's say preferably, if you see this set of work on the assessment report, you will see, okay, you can separate out the top and the bottom like x squared plus 2x plus 1 divided by x squared plus 2x plus 1. This will give you a 1. And then you need to subtract the 4x and recover x squared minus 2x plus 1. So you'll be able to get a 1 plus minus 4x divided by x plus 1 squared. Then the next thing is you may want to separate the minus 4x in this way, like minus 4 bracket x plus 1, and then you add 4 back to balance it out. And this term will be further reduced to minus 4 over x plus 1. And then the last term is just 4 over x plus 1 squared. And this is a set of a convincing working, but you do have to show the steps. Separating out the 1, treating the minus 4x, splitting in 2 terms, and then get the desired result. Or, insightfully, some student may observe that, x minus 1 divided by x plus 1 whole thing squared is the same as the ratio between 2 perfect squares. And then, instead of separating 2 quadratic expressions, they can just separate the ratio between 2 linear functions. Well, this becomes much handier because you can write x plus 1 minus 2 instead of, something like that. Then you will get a 1 minus 2 over x plus 1 whole thing squared. And this is, again, another perfect square pattern. So a minus b whole thing squared, which will be expanded to 1 squared minus 2 times 1 times 2 over x plus 1 plus 4 over x plus 1 squared. And therefore, you just nicely get, 1 minus 4 over x plus 1 plus 4 over x plus 1 squared with the a, b, c values matched. But painfully, we could observe that, after the first separation, we get the 1 here, and then we can deal with the minus 4x over x plus 1 squared separately, like putting in a partial fraction form. Eventually, by equating the numerators, you'll be able to find it. C is 4, B is minus 4, respectively. Alternatively, if you had no clue what's going on here, you may want to say, let's assume a equals to 1, b equals to minus 4, and c equals to 4. Well, this is sort of like a verification process rather than showing back to front. But it works because when you sub them in and combine them correctly, you'll be able to get x minus 1 squared divided by x plus 1 squared, which is equal to f of x. That confirmed a, b, c are the 3 values given to you. Part B, the graph of f has 1 turning point, so we want to find the coordinates of this turning point. Notice that f of x equals to x minus 1 squared divided by x plus 1 squared. It's a perfect square, greater than or equal to 0. The denominator cannot be 0, but the numerator is not cancelable, and it is possible to be 0 when x equals to 1. Also notice that the numerator alone is a non-cancelable repeated factor. Therefore, x equals to 1 gives you the minimum turning point at a 1, 0. But this is a 2 marks question. So if you just spot this is a 1, 0, you probably need to have some explanatory notes before your answer, like mentioning x minus 1 squared is a repeated factor, something like that. Well, actually, it is more natural to observe from part A, we can sub in the A, B, C value and write f of x in, let's say, negative index form. 1 minus 4, x plus 1, negative 1, plus 4, x plus 1 power negative 2. Then we can just differentiate to get f dash of x equals to 4, x plus 1 to the power minus 2. Take away 8, x plus 1 to the power negative 3, and it's equated to 0. Once you get that, you can write the equation in positive indexes, and you can cross multiply and cancel out x plus 1 squared. So you'll be able to get 4x plus 1 equals to 8 and x equals to 1. Therefore, the stationary point is 1, 0 as a pair of coordinates. So it involves some sort of a method, let's say a method mark for differentiation equated to 0. And then you attempt to solve this equation for x and get the full coordinates for the answer mark. Well, it is also possible to use quotient rule, but apparently it involves more work, more algebra, and it's more prone to making errors or silly mistakes. So you have to be very careful with your quotient rule, like x plus 1 squared, when you differentiate that, x minus 1 squared, what are you going to get after you differentiate the perfect square? And then just be mindful your denominator cannot be 0. You may want to isolate your numerator equal to 0 only. But the numerator itself after differentiation is not f dash of x. So you have to make sure you write the correct expression and equate to 0. Part C wants me to sketch the graph y equals to f of x, label the asymptotes with their equations, and the axial intercepts with their coordinates. So here, I'm not using a pen and paper to demonstrate how this graph can be sketched. Instead, I use the sequence of animations, but I will explain the procedure I would normally take. First of all, the asymptotes are x equals to minus 1 and y equals to 1. This can be observed from the partial fraction form because the number 1 is standalone, y equals to 1. Also, the denominator gives you x equals to minus 1. So you're going to put them down and label the equations. This is very important. And also, have you noticed the 2 points I put here? Well, remember, it is possible for any rational functions to cross their horizontal or oblique curvilinear asymptote, but definitely the rational functions will never cross any vertical asymptote. Therefore, this point should be a solid point rather than a hollow point, okay? Because the long-term behavior around the horizontal or oblique asymptote is far right or far left when x approaches to positive infinity or negative infinity. Next thing is 0, 1 is the y-intercept. 1, 0 is the turning point on the x-axis we obtained in part B. So we need to label them with correct coordinates. And just be mindful of the scale here. Look at the little grid. This is 0.5, half units per little grid. So your 1 unit is over there, okay? So you have to make sure you plot the y equals to 1 and 0, 1 at the correct places. Next thing is we pretty much see, okay, this is the behavior on the right side of this vertical asymptote. It has to, being convergent to x equals to minus 1 above. And then coming back to 0, 1, touches 1, 0, and come back again to approach the horizontal asymptote. You probably show a little bit inflective feature, slight inflection. Actually, there is a point of inflection at x equals to 2, but it was not required to be labeled or to state the coordinates. The bigger concern is on the left-hand side. We know it should look like some sort of hyperbola feature, but is that very close to the two asymptotes? Not really. You can actually do a couple of evaluations, subbing in, let's say, -2, -3, -4, -5, -6. Maybe 2 or 3 points will be enough. And subbing to the perfect square form, you will actually get some nice numbers. For example, -2, 9. Of course, this point is away from the available screen or set of axes here. So it's very high up. But when you sub in -3, you will be able to get a 4. So -3, 4. And then -4, 25 over 9. This is slightly lower than 3 because 27 over 9 is a 3. And eventually, when you get a -6, you'll be able to get a 49 over 25, which is tiny little bit below y equals to 2. With your evaluations, you can plot a couple of points here. And then it ensures you get the correct behavior and curvature of this graph. And then you use a single smooth stroke or single smooth curve to connect a couple of points you obtained. In fact, when you look at the graph on the assessment reports, yes, 1 mark was for a curve with the two asymptotes and a 0, 1, 1, 0 label cutting through these two places. And another mark, the second mark, is the right-hand side branch is completely correct, showing the correct turning point behavior. And the last mark is for the left-hand side. And you will see, okay, there is an error bar here, and there is another error bar here. So your curve needs to go through this error bar and this error bar, okay? Question 4. Consider the vectors A, B, and C. So first, we want to find the angle between A and B. So you can use a dot product if you want the angle between two vectors. Where do I get a 0, -3, -6 from? Well, vector A does not have an I component, and therefore it's a 0i, 3j, 3k. So it's 0 times 2. And -3 is 3 times -1, and 3 times -2 is -6. So this is A dot B. And then you multiply the magnitude and multiply cosine theta. That's the angle between A and B. So after some rearrangement, you get a cosine theta equals to -9 over root 18 times root 9, which is like, well, you can say -3 over 3 root 2, or let's say root 9 over root 18, but with a negative. And you will cancel this down to -1 over root 2. Remember, when your cosine theta is a negative value, this is an obtuse angle. So by convention, we find a 3 pi over 4. Of course, we don't want to say 5 pi over 4, even though it's the reflexive angle. By convention, when we talk about the angle between two vectors, we want to find anything between 0 to pi or 0 to 180 degrees. If you prefer degrees, please make sure you write degrees, okay? Not just 135 without unit specified. We don't know if it's 135 radians or 135 degrees. Find all possible values of n such that the dot product of AC is equal to the magnitude of the cross product of A and C. Notice the phrase, all possible values of n. That means your answer, the value of n, will be more than 1. So the dot product, it can be easily computed as a 9 if you take the dot product, but it involves more work to determine the cross product, and then you'll be able to get, let's say, some sort of a IJK notation. Okay, and eventually you get let's say 18n squared plus 9 equals to 81. And 18n squared is 72, n squared equals to 4. Therefore, n equals to plus or minus 2. Okay, so there are two values for this value n. Question 5 is a show that question. The curve with equation y equals to root k minus 1 over x squared for x larger than or equal to 1, but less than or equal to half k, and k is a number greater than 2. This curve is rotated about the x-axis to form a solid of revolution that has volume 7 pi over 2 units cubed. And we want to show that K satisfies this equation. So what you're going to do is first, you identify the I term involved. It's not the area. It's not the surface area by rotation. It's the volume of revolution. So you need to apply the correct formula. Say pi y squared dx with the limits 1 to half k. And yes, once you square the y, you get rid of the square root. This whole thing will be equated to 7 pi over 2. So your integration, integrate k gives you kx. Integrating minus 1 over x squared is plus 1 over x. So you raise the power from -2 to -1. And then you substitute 1 and a half k to get something along this line. And then the whole thing is also equal to 7 pi over 2, which means at some stage you may want to cancel out the pi from both sides. But initially, you still need the pi over there for constructing a volume expression. Next thing is once you canceled out the pi, you can actually push the 7 over 2 on the right and combine it. Okay, combine it. For example, in here, I did not combine it first. I actually multiplied everything by k to cancel out the k here. And then you will be able to push the 7 over 2k here and get a -9 over 2k. And the plus 2 has been relocated to the end. So we create a cubic expression in a descending order. And then multiply everything by 2. You will be able to get k cubed minus 2k squared minus 9k plus 4 equals to 0. So the 3 stages, one stage is constructing a volume expression. Second stage is you get an expression after integration involving k and or pi, and you equate that to 7 pi over 2. The last stage for the last mark is to simplify the whole equation and then manipulate the equation into the given answer. So that involves correct algebra working. Question 6 has a lot of reading. Put it simply, you have 3 stages for the production of a brand of a wheat trimmer. Stage 1, 2, 3 for W1, W2, W3, all in hours, the manufacturing time or production time. They are independent random variables assumed to be normally distributed. Stage 2 starts immediately after stage 1, and stage 3 starts immediately after stage 2 ends. And the table here just gives you the mean, standard deviation, and the cost at each stage. So you need to highlight the mean value and the standard deviation. By the way, if you want to use variance, it will be squared, okay? If you want the variance for each variable, you have to square each one, like 0.09, 0.16, 0.25. So first, the mean and the variance of the total production time for one wheat trimmer. This is just adding up the 3 mean values, but as I explained, if you add up the 3 variables and find the variance, you will need to add up their variances rather than simply adding up the standard deviation. So you need to square each individual standard deviation first, and then add them up. Eventually, you will get a nice number, which is 0.50. It involves more work when you want to find the total cost. Because when you look at the previous table, the cost is dollars per hour. So what's the cost? Total cost. So it's like $10 times W1, $20 times W2, and $15 times W3. That's why your cost function is 10W1, 20W2 plus 15W3. But when you want to find the variance, this is a combination, linear combination involving 3 dilation factors. So the combined variance will be 10 squared variance W1, 20 squared variance W2, and 225 times variance W3. Eventually, you can sub in the similar values you obtained or you used in part A. But the calculation of these will be a little bit problematic. But if you notice 100 times 0.09 is 9, 400 times 0.16 is 64. Then for the last number here, I would prefer using a fraction, 225 times a quarter. So the first whole number part is 73. The next part, 225, 4 does not go into 225, but 4 does go into 224. So I will split that out. 224 divided by 4 plus a quarter separately. So this is a whole number, 56, plus 73, that's 129. And add a quarter, you can write it like 129 a quarter, or 570 divided by 4. Or if you use decimal, that's fine. This is a terminating decimal, 129.25. The unit was not required, if I'm not mistaken, but you have to get the answer, the number correct. Either this form, or this form. Part C, if a single weed trimmer is produced, find the probability that the time spent at stage 2 will be less than the time spent at stage 1. Give your answer correct to 2 decimal places. And this rounding instruction probably rings a bell, because then you will see, using the standard normal z between -1 to 1, the probability is 0.68. Okay, this is a given fact, so you need to use that. Well, you could actually see, okay, it might have something to do with, 0.32 or 0.16. In fact, the answer is indeed 0.16. But to address the understanding, to demonstrate you really understood the question, you do have to do some conversions. Like, what does the question provide? It provides probability W2 is less than W1 equals to probability W2 minus W1 less than 0. So you can let W2 minus W1 equal to D, then the expected value is the difference between them. So 1.5 take 1.0 equals to half. And then the variance of D is the variance of W2 plus minus 1 squared times W1. So it will be 0.16 plus 0.09, which is 0.25. And this is 0.5 squared. That's why the standard deviation of this difference variable is 0.5. Then you are treating W2 minus W1 as one variable, so you are calculating D less than 0. And this is converting to Z less than 0, take the mean value, 0.5, divided by sigma. And eventually you are just finding an equivalent standard normal expression, probability Z less than -1, which is half of 0.32. And the answer is 0.16. Definitely, it is helpful to draw a normal diagram, but you really have to get the correct statement, and therefore, for the combined variable or difference variable, you need the standard deviation and also the expected value correct, and then show some working to arrive at the desired answer. Question 7 is a lovely separable differential equation question, but it's not like a ready-to-go form. You will have to push that to the other side. Let's say push the x to the other side, you get a minus x, then divide everything by root x squared plus 1. So 2y times dy dx equals to minus x divided by root x squared plus 1. And integrate both sides. You'll be able to get integral 2y dy equals to integral minus x root x squared plus 1 dx. And some will be able to directly spot, oh, this is a negative root x squared plus 1. But to be safer, it is not harmful to set out a clear substitution. Say, putting the u equal to the quadratic here, and your du dx is 2x. But on the top, you have a minus x times dx. Therefore, this will be minus half du, and the bottom will be square root of u. Left-hand side is ready to go y squared, apparently. But the right-hand side will give you a minus root u plus c. So to find C, I'm not going to put back the U first. I'm actually finding the corresponding value of U when X equals to 0. This comes from the initial condition. And then your Y will be -2. So -2 squared is 4, minus √1 plus C. So C equals to 5. When you get the correct C, put it back in explicitly in terms of Y and X. So you have Y squared equals to 5. Take away root X squared plus 1. But the question has 4 marks. So you probably need to mention a reason. Your initial Y value is -2, which is less than 0. So if you isolate Y, it can only be a negative square root rather than a positive square root. And the question did ask for Y as a function of X. So this is the final answer mark. Of course, this is some sort of standard approach. There will be some other more sophisticated approach, like using two definite integrals to solve this differential equation. And in the middle of the calculation, you can combine the integration and finding C together. But you do have to be aware of what change of variables here. This is required. Okay, if you were able to set up two definite integrals, make sure you use the correct order and also change a dummy variable in each integral. And then once you integrate everything, you will have to make sure your substitution, especially the plus or minuses, will be correctly executed. Okay, and it still leads to the same answer. Question 8. The relation is x squared y squared plus xy equals to 2, where xy are real numbers. So we use implicit differentiation to show that dy dx equals to minus y over x, given that 2xy is not equal to -1. So you probably would see that immediately after your implicit differentiation. But first, you have to use product and chain rule to get 4 terms, like x squared y squared when differentiated will give you 2 terms, like 2xy squared plus x squared times 2y dy dx. Remember, y is an implicit function of x. Chain rule applies. The next term, xy, gives you 1 times y plus x dy dx. And the right-hand side must be 0. If your right-hand side is not 0, you are not differentiating a constant correctly. And then you push the dy dx related terms to one side and the other terms on the left. Next thing is you can separate out or factorize out 2xy plus 1, which will then be divided throughout. So for example, the left side is now y times 2xy plus 1. The left side is a minus x, 2xy plus 1 again. So you may choose to cancel it here, or you can rearrange first and then cancel them out. But you do have to show how these two terms are canceled out explicitly, either in the middle of your rearrangement or after you divided everything and isolated your dy dx. I think the assessors need to see a clear factorization for the second mark to be awarded. Okay. Of course, it is lovely to see 2xy is not equal to -1 restated somewhere. Here is another, let's say, less than common approach. This method is called a partial differentiation. Well, I'm not intended to teach this thing, but I just want to mention. First, we could get a contour curve, or let's say multi-variable function, like we push the 2 to the other side, and we make whole chunk equal to 0. So the left-hand side chunk will be x squared, y squared plus xy minus 2. And here is a handy formula. This notation, this little curvy or italic d is called a partial derivative. So when we take the partial derivative, let's say we want to differentiate this function just with respect to x, then we will treat y as a constant. Similarly, if I differentiate this thing with respect to y, I will treat all the other letters involving x as a constant. That's why dy dx equals to negative partial fx divided by partial fy. It will be minus 2xy squared plus y on the top. divided by 2yx squared plus x. Then you can still get the same result by factorization and cancel it out. So you show the required result immediately. But this method, more than likely, only the UMAP students will know that. So stick to the standard approach we learned in 3-4 specialist math. Find all points on the graph where the slope of the tangent is equal to -1. Remember, this part B comes immediately after part A. What is the slope? The slope is given to you. So all you need to do is equate the slope to -1. And you'll be able to get -y over x equals to -1. So x must equal to y. But these points are along y equals to x. So where do these lines intersect the original curve? This is another point. We want the points on the curve, not just on y equals to x. So you will need to use this equation and sub into the original curve relation here. And you'll be able to get a biquadratic equation because this is x to the power 2 times x to the power 2 plus x times x. So you can isolate x squared as one item. And remember, in the substitution you made, you can see x squared now is your subject, but x must be real. That's why when you factorize out x squared plus 2, x squared minus 1, you will need to reject x squared equals to -2, all real numbers. And the only possibility will be x squared equals to 1. So when x equals to +1, y equals to +1. When x equals to -1, y equals to -1. Only 2 points, okay? 2 combinations. Therefore, the points will be 1, 1, and -1, -1, okay? Don't just do this question by guess and check. In the implicit differentiation question, when it involves some sort of coordinates, you want to find some coordinates. Remember, your original equation is your good friend. So don't just rely on one equation if it has 2 parts, x and y. You also need to solve a simultaneous equation by elimination or substitution. Question 9 involves a bit reading. So a car is traveling along a straight flat road. The velocity of the car and its position x kilometers are measured from the position on the road where x equals to 0. And the velocity and x are related by v squared equals to 1600 plus 672 over pi arc cosine x over 20. X is between -15 to 15 and v is greater than or equal to 0. So we have a speed detection device positioned to detect the speed of the car. As it passes the position x equals to 0, the speed limit on the road is 40. So the device will be activated if the car is traveling at 10% or more above the speed limit. So 10% of 40 is 4. So if the car is traveling at 44 or 44 above, larger than 44, then it will activate the speed detection device and you probably will receive a ticket, like an infringement notice. So we want to determine with evidence whether the speed detection device will be activated. So we convert the sentences into mathematical notation. If v is greater than or equal to 44, then the device will be activated. And at x equals to 0, we slot it in. So we'll be able to get a v squared equals to 1600 plus 672 divided by pi, arc cosine 0. So recognizing arc cos 0 is half pi, and then you will see 674 divided by 2. That is 336. Adding 1600, you get a 1936. And by the way, this number is exactly 44 squared. So at x equals to 0, yes, it reached the bottom line of the speed limit, the actual speed limit to activate the device. I think it's more reading, and then you do have to have some strong computational skill, like a basic number sense, okay? Subbing correct, and you need to know your exact value correctly. Next part, find the acceleration of the car when x equals to 12. Give your answer in the form k over pi. K is a whole number, which means you have to simplify the answer to this form. And the k could be a positive or negative integer, depending on our calculation. Directly, if you use A equals to the half V squared dx. This will be the most handy method. So what I'm saying is you pull out the half, or you want to multiply the half to get an 800 plus 336 over pi, arc cos x over 20, that's fine. But to get the fully correct answer, you need, let's say, a half, okay? Then half times 672 divided by pi times minus 1 over root 20 squared minus x squared. So you will see the relevant differentiation formula on the formula sheet, okay? So you have to correctly apply the differentiation here. And then if you sub in x equals to 12, this will be 336 divided by pi times minus 1. I should have a minus here. And then you will get a square root of 400 minus 144. So 336 over pi times minus 1 over root 256 will be multiplying by 1 over 16. And you cancel them out to get a minus 21 over pi, okay? Alternatively, if you prefer using v dv dx, well, it involves more work. And yes, eventually the square root expression will be canceled out, but you have to use the chain rule twice. Like the square root structure gives you half a reciprocal square root times the inner derivative. So this is more prone to error. Like sometimes you may miss multiplying by a v itself, or some sort of number errors in bits and pieces. So I wouldn't say v dv dx is an efficient method here. This is particularly important when you have a vx relation in terms of a square root. I would prefer half v squared ddx. Okay, finally, question 10. Question 10, last year, actually, a lot of students and teachers were unhappy with this question. Like, they've never seen a question like this before, like screw lines. But if I recall correctly, in the Cambridge Essential textbook and also Jacaranda textbook, there are some examples and exercise around this idea, skew lines, which means the two lines are running in two directions, but they are not crossing each other. They are just in a different planes. So it's a good idea to sketch a diagram of what's happening. So the two lines are skewed to each other. And to find the shortest distance between the two screw lines, we need a common perpendicular direction to both. So how do we find a common perpendicular direction? If you see my red arrow and a purple arrow here, these two arrows represent the direction of each line. For example, V1 is I plus 2j plus k. V2 is minus I plus 3j plus 2k. And if I repeat the process again, I'm shifting the first direction vector to meet the second direction vector. So now the direction doesn't change. It's still in the same direction. It's just a different start point. But now these two vectors are placed together. And then we can find, let's say, a common perpendicular vector to both directions. To find the common perpendicular or normal vector, we need to take the cross product. So this is the first important step. That's why we need a normal vector. A normal vector to both directions will be I minus 3j plus 5k, which you can find using cross product. The next thing is, how do I get the shortest distance? Well, with this vector pointing from, let's say, the purple line to the red line, this is a connecting vector. So we can choose one point from, let's say, the blue line, which is 1i 0j mk 10m. And also another point may well be 2 0 minus 1. Okay? And to find the connecting vector, we need to take a difference, let's say b minus a. So 2 minus 1 is 1, 0 minus 0 is still 0, and the minus 1 take m is minus m minus 1. So it's minus bracket m plus 1. So this is my vector AB here. And finally, we can extract just the connecting vector and the normal vector. And we can form a triangle. It's like a right angle triangle. And this right angle triangle, you will have the adjacent along the normal direction. And we can find the scalar resolute along the normal vector direction. And it represents the shortest distance. But I put the quotation mark here because a scalar resolute may well be negative rather than purely positive, okay? So in the next stage, for the shortest distance, yes, we do take the scalar resolute, but we will put an absolute value around this formula. It's A to B, AB dot n hat. What is n hat? The unit normal vector. So I will place this vector AB dot vector n, but divided by square root 1 plus 9 plus 25. So you square 1, square minus 3, square 5, and add together. This is the length. And you will find this square root is also root 35, which means you can pull out this 1 over root 35 and cancel it out from the right-hand side of the equation. And the next thing you do is just expand this dot product. You will get a minus 5m minus 4 within an absolute value. So this may well give you 5m plus 4 or minus 5m minus 4, either positive or negative. You don't have to square it when you remove an absolute value in real number operations. You just remove the absolute value and put plus or minus on the other side. And eventually you get a 5m equals to 10 or 5m equals to minus 18. And therefore m equals to 2, m equals to minus 18 over 5. The question says, find the values of m. There are two cases. As I explained, a scalar resolute may be positive or negative. That's why it has two possible m values. Okay, seems that that's towards the end of this recording, but I do want to mention there is a very brute force method, very brute force, not very viable within the exam time frame. I actually tried this method, and I sat in front of my desk and doodling around a piece of paper, and I give it a go a few times. Took me 25 minutes to sort that out. So I'll just outline what happens here. This method will be more suitable if you have CAS calculator, not in exam one, okay? If you encounter another similar question in future, like finding the distance between two screw lines or whatsoever, try not to use this method because this is just wasting your time, okay? And too much calculations involved. So basically, we can form a changing but a connecting vector between the two lines using the two positions. Take the difference between the two lines and then find the magnitude. So you can find a distance function involving two variables. Actually, it's three variables because you also have the m here. So the next thing is, once you're able to form, let's say, a square expression involving m, lambda, and the mu, you need other two equations to solve the system, okay? So we will use the vector joining the 2 points between line 1 and line 2 to take a dot product with the first velocity equal to 0, because it has to be perpendicular to both directions, both lines, to form a shortest distance. Similarly, I take R1, take R2 dot V2, and I get another equation. And after 2,000 years later, I'm able to find, let's say, some sort of a lambda value using this equation and another equation. For example, you can get a lambda value, then sub the lambda value into one of the equation to get a mu in terms of m. And eventually you push this equation and the lambda equals to 3 over 5 into the first equation involving the distance. And you need to square everything, so too much calculation. And eventually putting everything just in terms of m to cancel out the mu. And you need to it takes ages to recognize what actually happens here. It needs careful expansion to each perfect square. And you can see how large the numbers are. 875, 1400, minus 6,300 equals to 0. Of course, it's possible to divide everything by 25 and then do some factorization. Okay, 7m minus 14 and then 5m plus 18. Of course, you can also divide by 7 or whatsoever. And then you just find the same answer, but it's much longer. So stick to the scalar resolute method. And in future, if you find the distance from a point to a line or whatsoever, you will find this scalar resolute method is the most powerful method, or sometimes perpendicular resolute or whatsoever. Okay. All right. Hopefully you will find this video somewhat helpful. And thanks for watching. And I will see you in the near future. Bye bye.